Good evening. Welcome to the 19th Wright Colloquium. Topic this year, mathematics. So, of course, this is quite a peculiar situation given the pandemic. That's why this is going to be a live transmission on the Colloquium website. And the hall that I am now speaking from can host 600 people. Perhaps there are more than 600 people listening in at home behind your screens. So this evening and throughout this week, we should have been able to take part in scientific workshops organized by Science Co-op, an extension laboratory that collects experimental data. Given the situation, the workshops were recorded and will also be made available on the website. I am a scientific journalist and I will accompany you this evening along this trip of maths. So it's a scientific field, as you will understand, but it's also a field full of poetry. And this evening we're going to listen to Alain Connes, who's going to talk to us about the forms of music and the music of forms. It so happens that maths and music have a lot to do with one another. In the antiquity, music was considered to be a field of mathematics, but mathematics are also this very powerful toolbox which has enabled us to develop knowledge in the area of quantum physics. And Poincaré used to think that mathematics had a threefold purpose. First of all, to study the laws of nature, to come up with tools to study the laws of nature, then have a philosophical objective, but also an aesthetic objective. So this evening will be in two parts. We'll first listen to Professor Alain Connes' presentation for about 50 minutes, and then we'll have a Q&A session, which obviously you can take part in. And you can put questions on the Colloquium website. You have forms which appear on the right-hand side of the videos, so you have interpretation into English, and you can click on the icon below the video, and you can also put your questions in French or in English as you wish, and we will answer those questions during the Q&A session. Before we give the floor to Professor Connes, I'd like to give the floor to the president of the Wright Foundation that has been set up to encourage a dialogue between the public at large and the world of science and scientists. You have the floor, Mr. Courvoisier. Thank you, Sarah. Ladies and gentlemen, good evening. One of the ambitions of this week's Wright Colloquium of this week, is to relate mathematics with other achievements of the human brain. Up until now, we've done this with science, physics, and meteorology in particular. Tonight, it's art's turn, and we're going to conjugate art, mathematics as such, and the relationship between art, in the usual sense of the word, and mathematics, a very intense relationship when it comes to music, as Sarah's just reminded us. Alain Connes' presentation this evening is multifaceted and mixes up the relationship between music, forms, and mathematics. He's going to lead us a merry dance. So, with tremendous pleasure, I wish you a warm welcome. I imagine you're at home. I hope you've stocked up on your beer or other beverages, and I wish you again, as I said again, a warm welcome, and I'd like also to thank Professor Alain Connes for having accepted our invitation. Thank you very much, Mr. Conversier. Before we give the floor to Mr. Connes, I'd like to say a few words about Professor Connes. He was awarded the Fields Medal in 1982, the CNRS Prize in 2004. He's also a member of the Academy of Sciences. He teaches at the Collège de France. And to introduce him, I would like to give the floor to Élise Raphael, who's a mathematician at the University of Geneva, who's going to say also a few words about Professor Connes. Good evening. I'm very happy to present the speaker for this evening, a French mathematician. So I don't know if you were there yesterday evening. I don't have a lot of gossip or cheesy pictures from his childhood, but I'll start with his mathematics childhood. We don't give their birthdays, but we give the day in which they presented their thesis in 1963, and his scientific advisor was Jacques Dixmier. So he was particularly interested in von Neumann algebras. They're a bit wild, and they're various types 1, 2, 3, and in his dissertation, Alain Connes made it possible to classify the type 3 von Neumann algebras. He then linked them to more geometric objects, layers, and he was awarded the Fields Medal in 1982 for his contribution to the theory of operator algebras. Now, the main difference between the Fields Medal and the Nobel Prize is that Nobel Prize is for throughout a whole career, whereas the Fields Medal is awarded at the beginning of a career. So after having been awarded this medal in 1982, he continued to research and was awarded the Clay Prize in 2000 for having revolutionized the field of operator algebras, invented modern new non-commutative geometry, and discovered that his ideas crop up everywhere, including in the bases of theoretical physics. And this field, non-commutative geometry, complements other areas of mathematics. In 1984, he took over the chair Analysis and Geometry of the Collège de France to teach research while researching, and it's something he's been doing for 33 years. He gave a last course in 2017, Geometry and Quantum Physics. He also authored a very interesting work with Jean-Pierre Changeux. He published other books, for instance, as I said, the book with Jean-Pierre Changeux, Food for Thought, then with André Lichnerowitz and Marcel Paul Schutzenberger, Triangles of Thought. I think they're very interesting books, which I can thoroughly recommend. He's also wrote novels, Quantum Theatre, and the Atacama Spectrum. His characters are either physicists or mathematicians, and they're involved in research in space and the concepts that surround us. Obviously very close to his fields of research. He is a fantastic storyteller, and he takes us on fantastic adventures and develops beautiful concepts. And the music of forms is mentioned by the Atacama Ghost, and we will go on this trip this evening with Alain Connes, the music of forms. Alain Connes.
Thank you very much for this presentation. It really is a huge pleasure for me to be able to talk to you about the music of shapes. My presentation will be divided in several parts, and I shall start with the notion of spectrum. I'll talk about matrix mechanics as discovered by Heisenberg and the emergency of time. And in a second part I'll mention the spectral paradigm of geometry, non-commutative geometry at microscopic level in order to understand the fine structure of time-space, but also at larger scales, astronomical scales. Then we'll mention a musical shape, and then a diabolic or mysterious shape, and in the end I hope I'll be able to mention rhythmic patterns. So let's start with spectrum. The beginning of the story I'm going to tell you takes place in the 17th century. At the time of Newton, people started understanding that they could decompose light through a prism. We shall focus our interest on spectral lines. When the rainbow was divided into different colors, it was realized that certain places were missing, and Braunhofer, at the beginning of the 19th century, registered about 500 different spectral lines. Towards 1862, German chemists Bayesian and Birkhoff were able to produce the same lines, but as a kind of a negative version. There are what we call emission spectra. If you take natrium, for example, and you look at the light that goes through a prism, you obtain spectral lines that create a kind of barcode which is totally specific to that specific chemical product. These chemists understood that most spectral lines were connected, these barcodes were connected to chemical products, and they invented a new chemical body called helium, which was supposed to have a specific barcode, and miraculously at the beginning of the 19th century, 20th century, during the eruption of the Vesuvium, analyses were made, and helium was indeed confirmed as having that kind of spectral lines. Chemists and physicists studied these spectral lines and observed that there was Rydberg's law. When expressed in form of frequencies, not in terms of wavelengths, certain spectral lines add up to give a new spectral line. And they understood that if you want to understand that kind of law, you had to use not one index, alpha or beta, but two indices. If you study spectral lines under that point of view, you realize that certain lines are the addition of two different spectral lines. This was a miraculous, a wonderful discovery that was made thanks to Heisenberg. Heisenberg understood that this law of composition, which is called Rydberg's law, led immediately, if you're a physicist and you concentrate on observable values, led to matrix mechanics. Of course, mathematicians know about that, but not physicists. If you make a product of two matrices, you use precisely this Rydberg law. You obtain the ik from the sum of ij and jk. The discovery of Heisenberg was that these matrices were not commuting. He had hay fever and he was sent to the island of Helgoland. And when he was there, this island has no pollen whatsoever, so he was sent there to cure his hay fever, and of course he used his time to do research. He had no teaching to do, and towards 4 in the morning one night he discovered and he saw in front of his eyes a wonderful landscape where he was able to climb on a peak of this island, and he waited for the sun to rise. And there is even a stele which is has been built there to celebrate this splendid discovery in 1925. What Heisenberg discovered was that if you manipulate observable quantities for a microscopic system, the order of the terms has a vital part to play. E equals mc squared. But you can't inverse the terms of this equation in this specific case. Commutativity does no longer hold in the phases of a microscopic system. This might be a difficult challenge, but we tend to know that kind of phenomenon because when we write things down using language, we know that we have to take into account the order in which we write the letters. If we don't, we have sometimes the cases of anagrams. In other words, if you invert the letters, you can have sometimes a different sentence. If you go from the quantum world to the normal world, you lose meaning sometimes, because for example the two sentences you see here have actually exactly the same content in the commutative world. So going into a non-commutative means losing meaning. My interest for this topic comes from the fact that von Neumann, who was one of the most important mathematicians of this century, codified the mechanism of quantum mechanics and studied subsystems of it. I, for one, started my scientific career in my PhD, directed by Jacques Dixmier, by discovering that for von Neumann algebra there was a totally canonical evolution, and two Japanese mathematicians had understood already before that there was a link between the Heisenberg evolution and another state. And what I showed in my PhD thesis was that this evolution was independent of the state as long as you use internal heteromorphisms. From then came the idea that the non-commutativity was sort of the root of evolution and of the emergence of time. After working on that, on classifying factors, as I did in my PhD thesis, and the reduction from the type 3 to type 2. Type 3 was something quite mysterious at the time. I understood that there was a way of associating lamination, which is a very natural mathematical object, to a non-commutative space, and that I was therefore compelled to invent a specific geometry where spaces where coordinates do not commute. And what I'm going to try and show you is the way this geometry, this spectral geometry, is intricately linked to formalism of quantum mechanics. And for that you have to quote a sentence by Riemann. When Riemann gave his inaugural speech, he was extremely clairvoyant, because he understood that even geometry, as was proposed, was not necessarily the geometry that would be valid if you concentrate on the infinitely small scale. And he said very clearly that for very small distances, atom scales, it's impossible to talk about rigid bodies. And Riemann wrote explicitly that the reality on which space is based creates discrete diversity, or that the basis of metrics relations can be looked for outside of this space. It is said that the distance between 2 points is calculated by the shortest possible distance or path between these 2 points. But what Riemann says is mentioning the square of this distance, as can be illustrated by this geographical map between Seattle and London. But it has also been illustrated by what happened during the French Revolution, when they wanted to introduce or unify the unit of length by introducing the metric system. Beforehand, a fabric merchant who traveled from the north to the south of France encountered many different ways of calculating length. So two physicists, Delambre and Méchain, triangulated the distance between Dunkirk and Barcelona. All sorts of interesting stories happened to them. They used a telescope and went up hills, and they had great difficulties to explain to the Spaniards, who were at war with the French, that there were no spies. But finally they made it, and they defined through a platinum bar what was the unit of length. This unit of length was supposed to be the 40 millionth part of the terrestrial meridian. But what was interesting to know is that the evolution of this unit of length introduced by the French Revolution and the evolution to the definition that we now have is exactly parallel to the evolution that we had between Riemann and non-commutative geometry. Towards 1925, very clever physicists realized that this platinum stick, which was supposed to have a certain length, changed its length. And they noticed that by comparing the length of this stick with the length of the wavelength of krypton, and they realized that the length of the stick was not constant. Many years later, in 1960, it was understood that the meter had to be redefined, taking as a basis the wavelength of the krypton. But in the meantime, we even realized that there was an even better way of explaining this length by using the transition phase of cesium. And you can even buy in shops, in specialized shops, tool that can give you a very, very precise measurement scale. This way of measuring length is spectral. The length of the wavelength of the cesium is 3.26 centimeters and doesn't change. If you wanted, for example, to unify the metric system in the whole of our galaxy, and you couldn't possibly ask aliens to come back from far away and go to Paris and measure their length of their unit of length with the platinum stick. However, you could possibly transmit or send them in a codified way the idea of the transition between these two levels of the state of atom of cesium. They would have exactly the same measurement. So it's a radical change. And that was made possible in non-commutative geometry. And it was made possible, if you look at it very closely, because it was possible to extract the square root of Riemann's ds2. This was made thanks to operators and using what is called Clifford's method, and it was done by Dirac. What's important to know is that in this new paradigm, the element of length is an operator, and this element of length is interesting, is given through its spectrum, and it's the non-commutativity of Clifford's algebra enables you to say that a sum of a square is itself a square, which is quite surprising. If you write x plus y to the square equals x to the square plus y to the square. The measurement of length is totally dual, and you obtain it by sending a wave to a certain point and by bounding this frequency and looking at the dephasing. And that's what you call the Kantorovich dual. Obviously, there is a dictionary which goes from classical algebra to quantum methods. What's important is to know that in this new formalism, it's quite possible to follow the way the quantum approach introduces very subtle nuances. That's what physicists call the closed propagator. As a function of h bar, Planck's constant. And what's wonderful in this formalism of geometry, starting from this element of length, which is an operator, is that you can follow its change. What was obtained in that way is a new geometrical paradigm in which the scene is given by Hilbert's space, which is a wonderful space, infinitely wide. There is also an involutive algebra representing the space, and you have the element of length, which is given by the inverse of value of the self-adjoint operator D. What's important is to illustrate this principle with all sorts of examples. But what was demonstrated by my collaborator Jean-Céline is that thanks to this freeing of geometry through the spectral observation, space-time has a fine structure which enables us to understand the Braut-Englert field and the standard model. Now, the most challenging part is, as a matter of fact, quite easy to explain, and it comes from the idea that just like with Dirac's operator, combine the components of momentum, you had to combine position variables in the same way. And therefore you could re-establish all sorts of symmetries. And you get the feeling that you understand space-time at a microscopic level in a much more subtle way. And this corresponds entirely to Riemann's idea, because this fine structure corresponds to the forces that bind atoms together. So the sentence that he wrote down was incredibly prophetic. This explains what's happening at short distances. So the question might be asked, why should we complicate our lives for astronomical distances? And does the whole problem change if we are interested at a much wider scale? So my question is actually, where are we? Are we able to transmit to other civilizations in the universe the coordinates of the place where we are? If we tell them, for example, that we're going to give them coordinates in the system of coordinates, that would be ridiculous, because if you want a system of coordinates, you should find an original point. So this is a very interesting problem with two mathematical sides. The first one is it possible to specify a shape through a list of invariants, something that doesn't change with the choice of the original point? And then, is it possible to specify in an invariant way a point in a geometric space? When a rocket was sent into space in this Pioneer rocket, it's possible to show the solar system with planets, etc. But the solution that was found for this was quite close to the one I mentioned. They show various directions, and for each of these directions a different frequency. It's not very far from the answer that should be given to this question, where are we? The answer is indeed spectral. And two important papers have been written on this issue. The first one is Mark Katz's Can One Hear the Shape of a Drum? Is the first one. Is it possible to reconstitute the shape of a drum by listening to it? And the second paper is the one from John Milner, a one-page paper, where he shows that the natural invariant of a shape given by its spectrum, I explained to you why, is not enough to characterize the shape. You have to know slightly more about it. You have to know the chords and not only the scale in musical terms. If you take a disc, for example, this disc is going to have all sorts of own frequencies and specific frequencies. I'm going to try and show you what they look like if you can listen to them. If you take this disc, for example, the frequencies of this disc will depend on two data. A data which is the number or the change when you go round the disc. Here, for example, you have 5. And then there is another number, which is the number of vibrations. The more you go far away, the further you go away from the center. The note you can hear is higher. A specific disc has what we call a spectrum, which is a scale canonically associated and which can be calculated in mathematical terms, and has also a spectrum that you can see going from infrared to ultraviolet. So mathematicians discovered that it's just not possible to characterize a space through the data of its scale. I showed you the disk and the specific frequencies of disks, which characterize the shape. When there is a shape of dimension 2, you obtain a parabole. But what's important is that you can find examples of shapes having the same spectrum, but which are different. After the example of Milner in 16 dimensions, Gordon, Webb and Wolpert found out a very, very simple example in 2 dimensions. And to show you the invariant that is used, I'll take a very tangible example. The first shape is made up of a triangle and a square. And the second shape is the union of a triangle and a rectangle. When you make the calculations, you realize that these 2 shapes have exactly the same spectrum. So their spectrum is entirely identical. But if you look closer, you notice that the notes belong to 3 different types, with the differences of 1/2, 1/3, or nothing at all. And therefore, you obtain a kind of scale like on a piano, where you have black and white touches. The 2 scales are exactly the same, the notes are the same, but there is a fundamental difference between the 2 shapes. A chord is possible on one shape, but blue-red chord is impossible in shape 2. I'm not going into the details, but you have to understand that there is a lack of possibility to specify chords. For invariance, there are 2 important things, the spectrum and the relative spectrum. It's fairly difficult to define, but it enables you to define a point. A point will be given through possible correlations between frequencies. You see that for the second shape, it was impossible to have a correlation between the blue note and the red note. So there are correlations between frequencies, but if you think about it, our perception of a faraway space is governed by these correlations between different wavelengths. If you look at the Milky Way, we look at it through infrared, and you notice the difference in perception of these wavelengths. in summary, there is something extremely powerful in spectra, and the universe communicates with us by sending us barcodes. It communicates with us through barcodes by sending us messages that are composed of barcodes. A very well-known example is the red shift, which helped us understand the composition of the universe. But that was sent through these spectra and barcodes that were shifted towards the red. And now let me turn to a musical shape. Of course, it's very tempting when you have that kind of association between a shape and a scale to try and look for a shape in the scale with which you can play music. You believe that, to start with, that the scale would be 1, 2, 3, 4, 5, with frequencies corresponding to a small piece of string. But that doesn't work. It doesn't correspond in the end. The reason being that our ear is sensitive to the multiplication by 2, not by adding 1, but you have to multiply by 2, and if you do so, you obtain a different note, and this is the octave. If you touch the D note, you obtain the same D note, but an octave higher. It's very interesting to look at a guitar to understand what's happening, because if you see the pieces of the guitar, the elements with which the guitar is composed, these are not equal. You have a spectrum there on the handle of the guitar. And without having to look into books, you always have to ask very direct questions. And then you notice that this spectrum is made up of powers of a number. Which is this number? Well, this number is the reason why classical music exists. It's the power 1/12 of the number 2, which is more or less the same thing as the power 1 to the 19th, 1 divided by 19 of the number 3. The quasi-equality between these two numbers creates harmony and enables you, for example, to have works of music, classical music, to do as if these figures were musical notes. So the scale you have are powers of these numbers, as you can see on a guitar. It's interesting to know and understand what it means in musical terms, and therefore it's worth wondering how it's possible to have that musical shape with which we can play the same piece of music starting from any point. Let's start with number 13, for example.
So, if I had chosen another number, I wouldn't have had to do anything. It would have been exactly the same. So if I use 14, so obviously, the obvious question that comes to mind is to find out if there's a form that matches this spectrum. And this kind of question is going to come up. And when you look at various areas and it doesn't work. Why? Because the spectrum explains that the form that what we're looking for is 0. And the reason we understand this is because we see this via the spectrum that is growing exponentially, because it's the same number, various powers. So the dimension obviously has to be 0, so there's a fantastic answer, a quantum sphere, which is a spectral triplet, and it has a fantastic advantage compared to other possible solutions. It's perfectly symmetrical. It has a quantum group of symmetry that manages its geometry. So I'm now going to talk to you about something which is absolutely devilish, which I'm going to call non-identified form. And for those who are specialists, they will see the zeros of the Riemann function, and they appear very naturally, as in the vertical, around 14, and then they repeat in a symmetrical fashion. So this gives us a spectrum, and this spectrum can be looked at, and we see that it's very, very difficult and delicate. And mathematicians, Selberg, have tried to build a surface, which I'm going to try and show you. This is a surface which he built, which comes close to it, but there's a minus sign, which indicates a huge difficulty to build this spectrum, and the reason why I wanted to explain why I called it devilish. It's the recent work with Katia Consani. We've built this non-commutative geometric object which is being built and given dimension which tends towards the infinite. But it's really a spectral triplet, and all the conditions have been checked. It's an interval with a new geometry. And when we calculated the spectrum and compared to the other spectrum, we were quite spellbound by the matching between the two. Not exactly the same for mathematical reasons, because we looked at the asymptotic development. But what's absolutely devilish, diabolical, I mean, if you don't pay attention, if you look further in the frequencies, you have the feeling that it's not going to work. So you come back to your starting point, and when you work in this area, you have the feeling that you're playing chess with the devil. So this is the spectrum that we arrived at, which is very similar. And a couple of years ago, with Jacques Dismier and Dany Chéreau, my wife, we wrote this novel, the Spectre d'Atacama, and all sorts of adventures happen to the hero of the book. He's fascinated by a spectrum which he cannot identify. He's at St. Helena, and he's trying to compare the spectral frequencies with Napoleon's war dates. So we are emphasizing in this work this fantastic method for mathematicians, i.e., when they have a problem that they cannot solve, they generalize the problem to such a way they can then look at a more simple case, which then will be solved and which will give them an idea to solve more complicated problems. This is the chocolate slab, and if you ask how many squares and how many times you have to break the squares to be able to eat one square, and if you go about the problem as a mathematician, what are you going to do? You're going to generalize the problem by saying that the length is n and width is m, and then you'll start at very small m's and n's. And mathematicians who cannot understand this mysterious spectrum, they've generalized it and have been able to show that the analog of Riemann's conjecture was correct, but in a more simple case, the case of functions. And in our book, in our novel, the hero manages to understand that the spectrum that was sent to him was the devilish or mysterious spectrum, and he tries, we finally understand that this is no doubt due to a celestial object that is perhaps inhabited by intelligent beings, and to be able to show, to prove that these beings are intelligent, you send them the Turing test, so they use the result, and to send the result with a laser beam, but in the form of a rhythm. So the result shows that the natural significance of the frequencies is time, a dual time, which is easy to understand in physics between time and frequencies. And this duality has led us to illustrate the result, not by music, not by a tune with different frequencies, etc., but what we call a rhythmic motif. And we were absolutely spellbound to see that the symmetry, which is natural in Bayes' theory, is repeated in these rhythmic motifs that have been invented by Olivier Messiaen in his work. And this allowed us to communicate, and obviously in the book, in the novel, we send out rhythms which correspond to whole numbers, and so we're absolutely certain when they send us back similar whole numbers that we understand that they are intelligent human beings and not a machine. And I'm going to show you an illustration of the music, which is based on whole numbers and created in such a way as to say nothing else but the data of the whole number in this language of the scale, in the scalar language. And I'm just going to ask you to listen to this music and show you the picture, so that in the uppermost rectangle you have all the numbers when you've taken out the multiples of 2 and 3 and the multiples of 5. So these two rectangles, 60 by 60, and now what we're going to do is that slowly but surely we're going to take out all the dancers, because this is choreography. We take out the multiple of the whole number, number 7, to start off with. And when we see the dancers come down to the lower rectangle, you'll listen to the music which corresponds to the 7. So we have now the last four and now the last two that are coming down. The last two that are coming down now. And they're going to take up position. And these are the whole numbers until 3,600. There we are. I'll let you listen. Thank you very much, Alain Connes, for this brilliant presentation. It's quite extraordinary. So now we're going on to our Q&A session, and we're going to have with us Elise Raphael, Professor Hera, and we have Shaula Sialefi, who's going to read out the questions. So whilst we're waiting for the first questions from the audience, this music of whole numbers reminded me to what extent Olivier Messiaens had played an essential role in your work. I know that you've written scientific articles and more extension-orientated work. Perhaps you could tell us more? Well, I hope you can still hear me. Yes? Yes, we hear you very well, sir. So it's quite a funny story, in fact. The problem that I mentioned earlier on, in the spectral interpretation that I'd given many moons ago, what was obvious is that zeros appeared as times, unlike what we used to understand them as, i.e. forms of energy. And what's rather interesting, and when you look at the case that was solved by Weil, we realize that zeros have a periodic disposition. So let's take energy for the dispersion of periodic elements. It's quite a natural phenomenon because there is periodicity in time. So when we wrote our novel with Danny Chéreau and Jacques Dixmier, we realized when we were writing the book that if we consider zeros in the way that Weil had considered them and consider them as elements of time, we find a way of playing music which is associated with a curve associated with a finite object. But what's extraordinary, so I wrote an article in a review of music. Rhythmic motifs. It's rather fun because the motif is a mathematical element. So I'm going to show you a video clip which is to do with the rhythmic read, because I said these whole numbers were calculated mathematically. So you need a score, but I'm going to show you this on my screen. You need a score, a music score, that matches the whole numbers. So it was not that easy to do. I used the scale of the different powers, 1 to the power 19, and then I calculated the development of the square roots of the whole numbers. So for every whole new number, I got a score. But it's presented in a canonic way, and I'll give you a few examples. So when you look at the score, this is the one for 7, 11, 13. And when you look at the score, you see that it's perfectly symmetrical. And this symmetry is to be found in Messiaen's work. So then you have to see this symmetry in the rhythm. And what happens when you look at these rhythms is rather interesting, because when you calculate the zeros and the curves that are associated with the whole numbers, you come to realize that the symmetry of Messiaen appears in the rhythm, which is rather extraordinary. And the result is that, first of all, you have the theme. You're going to play the theme using the rhythm which has been given you in a very natural fashion by the curve based on the individual whole numbers. So this is, in fact, a video clip which is a natural follow-on of the video clip I showed you earlier on. And you will see the way in which the zeros are spread out. It's like a rhythmic game which is going to apply to the whole numbers and belong to an object, which is a curve which allows you to calculate these rhythms. I'm going to try and show you this video clip. So, we start off with the video I showed you earlier on. The last picture of the video clip I showed you earlier on. In the uppermost rectangle, you had the whole numbers, the residual whole numbers, when you've brought down all the other preceding numbers. And now we are going to listen to what happens when you play these whole numbers. Before I played them in a regular fashion, now we're going to play them in a irregular fashion, following the rhythmic motif. So you see what happens is that we have a vision of these zeros which correspond to these elements, but we have also something extraordinary. Every time the hyperelliptic curve, we see there's something that is similar in all the rhythms that have to do with the first rhythm. We can go to another curve which is different, like this one, and this one. Yes, we can hear the difference between the two. Well, you hear the difference, and what's quite strange is some curves are somewhat jazzy and others are not at all jazzy. And it's very consistent. That's what's so strange. I'm going to stop my screen share. There's some sort of consistency there, which means that the corresponding curves come from the first hyperelliptic curve, which is the reduction of the whole numbers. So what I tried to show you in my presentation, that at the end of the day we have extraordinary tools. We have a visual tool and we have also an audio tool. And with the visual tool you can compare spectra, etc. But with the audio tool, the difference between the two is that the audio tool you have to listen in several times before you can really understand the hidden secret, whereas in the visual tool you see immediately what's happening. Immediately. Quasi-immediately. I didn't want to interrupt you, I apologize. But I'd also like to mention this aspects to do with quantum physics that permeates your work. I mean, during the week, several speakers mentioned these close links between mathematics and physics. And I was wondering why. I mean, when you're a mathematician, we are so interested in physics. I mean, do we see physics as a source of mathematical problems that need to be solved, or do we consider mathematics have their own language? And I would have liked to understand your viewpoint, Alain Connes. Well, my viewpoint is that of a heretic, pure heresy, because as far as I'm concerned, the real world started off with mathematics. So I've come to the point where I think, I mean, very naively, there are lots of naive people who don't do mathematics and they think that mathematics exists in the real world. I don't share that viewpoint at all. I have the opposite viewpoint, a dual viewpoint, because as far as I'm concerned, if you work in the field of mathematics and you look for specific numbers, you won't find them. But what I've noticed over the years, that you have crucial data from the real world, but you can find them in the field of mathematics. And that's what I mentioned in my dissertation, the emergence of space-time. And I've come to the viewpoint, which is very strange, peculiar indeed, i.e. that the real world started off with mathematics, and our very existence is a sort of window on this real world. And this gives us a glimpse of eternity, and have the feeling of eternity, and it allows us to forget that we are terrestrial beings, and that's how I perceive the link between mathematics and physics. I know it's very strange, very peculiar, and difficult to understand, but rather poetic, may I say. And is this an opinion that you would agree with? I'm turning to the other panel members. I'm not a physicist. I only deal with pure mathematics, and I have the feeling that a lot of people complain that the problems that I was working on had nothing to do with physics. It doesn't upset me at all. I found these problems extraordinary, very beautiful as such, and I don't need to find mathematics in the real world, as says Alain Connes. I don't need to find my mathematical problems in the real world to find them beautiful, but I can understand that the people are more interested when there are practical applications. But I like the idea that they come from mathematical considerations or mathematical curiosity. I think that Alain's viewpoint is quite radical. I don't know if I'm ready to agree with him. Maybe I might say things differently, just as radically, for instance. One could put it this way, i.e. that mathematics is a universe, it's a tool, a universal tool, and if you look at the relationship between mathematics and physics, at the end of the day, we mathematicians believe then we can do physics better than physicists. I don't know if it's still true. It's perhaps a conjecture that needs to be proved, but I think it's a good viewpoint, and that's mine. Chevalier, have we got questions from the audience? Yes, quite a few. Several questions that have asked us if there are links between non-commutative geometry and other things that may vibrate, or the string theory, or general relativity. Well, it doesn't vibrate that much, but perhaps there are links nevertheless, or with loop quantum gravity, or... That's a good question. Yes, because when I was preparing for this evening, I realized that non-commutativity often is associated with this attempt by physicists to describe the whole. So it'd be interesting to hear what you have to say about all that. Well, I shall answer by starting with the link with gravitation. I wasn't able to go into details for lack of time, but what I did with my colleague Shamsuddin, we were able to show that if we make space-time geometry slightly more subtle, but to explain it generally, if you want a simple model, let's say you have space, two-dimensional space. So instead of thinking of a piece of paper, you look at it from one side. If you look at it from both sides, when you look at a function, you'll be able to differentiate it one side, differentiate it the other side, but you'll also be able to get the finite differentiation between the top and the bottom. And this gives you the Hills space. But in fact, there were three of them involved in the discovery. And what's rather surprising, as I said earlier on, when you think about it, that if you make the texture slightly more subtle, space-time, and if you look at the pure gravitation of this new space, you're not only going to get gravitation, but you're also going to get gravitation with non-standard forces. And when you think about it, and you introduce this way of trying to explain all the coordinates with one single data, you find the models, non-standard models. So you're going to say, what is the function of the axiom? Well, it depends on the element of length that I described, and this element of length, which corresponds to what Riemann said, there's matrix of Fukawa, the coupling, which corresponds to the quantities you find in the model, in the standard model. So the link with gravitation is developed in such a way that the pure gravitation of the new space is going to give you the coupling spaces of the standard models, but it is in fact a very naive viewpoint. So the link with string theory, yes, of course there is a link, and I remember in 1986 I attended the conference at Berkeley, and during this conference it was suggested the open string theory, and this function will use the non-commutative geometry. And afterwards, I wrote a paper on the string theory, and which is in fact very often quoted, which I co-wrote with Albert Schwartz and Michael Douglas. And my contribution was as follows. One day, with Albert Schwartz, we were going down to get some tea, and he asked me a question, and I had the answer in my pocket, and that's how I contributed this article. It's the most often quoted article when it comes to my name. So there's a link with the string theory, insofar as the model that I gave you early on of the space-time model in non-commutative form, the fine structure that you add on is made of the 6 dimensions. So when you calculate dimension, the chaos theory, which is very complicated and developed, 6 dimension means that total dimension is 6 plus 4, i.e. 10, like in the string theory. So for the time being, nobody has understood what's behind this coincidence, but there is a potential link with the string theory. Now, I do not share all the philosophy behind the string theory, but that's the link. The link with the loop theory, well, there's none to my mind. I don't like criticizing theories that are put forward, but I spent a number of years working on this with Durkheim, and I think that a theory can only be interesting in the world of physics, because if you've got non-commutative geometry involved. So I'm a bit skeptical of those theories that don't include that aspect and that don't use this fantastic discovery of physicists. So that's my viewpoint on that subject.
Let's come back to music, but maybe also let's talk about literature and your research activity. You've written many novels based on science, and I have the impression that many mathematicians share a very privileged relationship with arts, music or literature. And why did you choose to write? To which extent do your novels take into account your research and vice versa? Do you write novels on the basis of your research and vice versa? Well, yes, indeed, my novels are fed with my research work. But it's also true that the proximity I kept with my PhD professor was also something important, because he wrote science fiction novels and detective novels. And the story of one of his books is very interesting. One day we were where I am now in my secondary home in the Perche region, and I received a postcard. I've got the title of the novel, please write the whole novel, and I correct the proof. I'll do the proofreading. That was rather funny. I had just received from Etienne Klein this wonderful anagram, which I showed, which says in French, in one way, clock of angels, in the other form, Higgs boson. At the beginning, it was considered to be a kind of joke, but my wife and I went to Venice for a holiday, and we went to a palace where there was an exhibition with a sculpture by Catalan, fairly well-known Italian sculptor. And this sculpture was of 9 corpses next to each other, as large as life. And it was at the time when a prize had been awarded to physicists for their work as physicists. And I made the connection. And I had started to write a novel with a formidable beginning, where there was a visitor looking at the sculpture and feeling or smelling something particular. And police had been called in, and I'd shown this extract to my wife, and she said, what you've written is absolutely awful. So she had started writing something different, and her scenario started differently. There was a physicist, a French physicist, received a phone call from the Italian, from someone who proposed her to be the director of CERN. After the publication of the book, Fabiella Giannotti became, indeed, as an Italian woman, the first director of CERN. So I thought that was a funny coincidence. Obviously, this book was based on mathematical thought. And in particular, we try in this book to explain the story of emergence of time. And there is a rather critical sentence there, but which may have meaning, where we try to explain how time comes from quantum theory. In quantum randomness, you have several Swiss engineers who have made up a tool with which you can fabricate something which is quantic. As you know, it's impossible to predict the place where a photon will land. And this randomness is totally irreducible. We know it from theory, we know it from experiments. But this quantum randomness is absolutely fascinating. What we try to explain in this novel is that this quantum randomness is at the origin of time. This theory has a mathematical basis, but philosophically I wasn't able to convince people that it was true. It's very difficult to go from the mathematical point of view to the philosophical point of view. It goes in that direction, but I can't tell you that in the other direction it's also true. Writing novels does influence me, but it's not sufficiently to lead me to research. But what's more important for me is music, playing the piano, for example. That is sufficient for me. Being confronted with musical writing is a source of enrichment for me. I'm not a good pianist, I'm not able to play properly Chopin. But what I like is reading musical scores. Studying a musical score, even slowly, is something that is extremely enriching for me, because I feel in that writing something so subtle that it goes far beyond any other forms of subtlety. When I feel nuances that are incredibly well chosen, for example, which have repercussions, that is something that I find fascinating. Thank you very much. It's extremely interesting, because in your books we get the impression of philosophical essays more than vulgarization books. Do we have other questions from the audience? Yes, quite a recent one. You've talked about thermal time. How is it possible to conceive a universe without time, or before the birth of time? Well, that's a wonderful question, because it is indeed dealt with in the book I've just mentioned and in the two books I wrote, because there is an echo in the second book. This question, I think, can be answered in the following way. The emergence of time, as I mentioned, comes from a partial knowledge of a quantum system. Von Neumann studied subsystems of a system, and this is the way he invented von Neumann's algebra. A subsystem is given by a factor, what you call a factor, which is something that looks like a factorization of Hilbert space, but which is more subtle than that. That's what you call a factor. So what's extraordinary is that factors of type 3 have a specific property. They have their own time. But where does it come from? Well, from the fact that we only have a partial knowledge of the quantum system in question. Disappearance of time is total knowledge for me. So in my novel, there is an experiment made by Charlotte, and Charlotte has an apocalyptic experience on herself. Her brain is totally encoded in the huge computers at CERN. So her brain is entirely caught by these computers. She sits in one of the colliders, and that happens. She's supposed to die. Her body is brought down at very low temperatures, but she resuscitates in the end. As a matter of fact, she has been resuscitated by her brain, which remained alive. human being dies whenever their brain dies. But this is not the case for Charlotte. In the end, at the end of the story, she resuscitates. And then she tried to explain to people around her the experience that she had when she was more or less dead. There was no time any longer. She had that kind of vision, which she tried to explain through a poem from a Swedish poet. She tried to explain that kind of vision she had of a world without time. Well, I don't know as a writer if I succeeded, but in any case, in my two books, I tried to show that kind of experience and to show that you can dream about it. What would indeed be a world where we wouldn't have a partial knowledge, but a global, total knowledge of everything. That would mean the end of time. Well, let's go back to quantum theater, which you've started explaining. The lead character is a physicist, as you said, and this reminded me of what was said by my colleague when we welcomed Laure Saint-Raymond on Tuesday. What is the place of women in mathematics? Do you have an opinion? Do you think that more women, or more measures should be taken to include more women in mathematics? Well, I have many women collaborators. I work with Katia Cantiani, for example, for the time being. Well, this is a rather subtle situation, and one shouldn't make any mistakes there. Mrs. Serre had the idea of join the two écoles normales, because in France there used to be one for boys and one for girls. It sounded or looked like a very good idea, coming from a woman and coming from one who was really a great talent. But the problem was, what happened afterwards was that indeed there was a kind of equality between the sexes. But 2 or 3 years ago, not one single girl got a PhD. Inversely, introducing quotas or things like that is totally despicable. Girls who turn to mathematics are very often much more gifted than boys, so they don't need to be supported through quotas. The problem arises much earlier at the level of secondary schools or just before you enter the university. I remember the time when I was there, there were many girls with me, but at the time, that's the way it goes. They are brilliant just up to the time of their baccalaureate. But then afterwards they choose rather biology or literature, and very rarely do they choose to study mathematics. And I think the main problem is linked with this point in time in their career, not later on when they have already entered university, but much earlier, before they enter university. Naive solutions do not work, even with the best intentions in the world. You'll reach a situation which will be exactly the contrary of what you're looking for. But what I can tell you is that women who succeed in mathematics are absolutely brilliant. Alice, what's your point of view? Do you have something to add there? Well, it's easy to agree with the idea that quota is counterproductive. Quota create a bias for women. They wonder whether they are there or they have been chosen because they deserve it or because they benefited from a quota. Sometimes we were asked when we were writing our PhD whether we were there because we benefited from a kind of support, and that's exactly the case I am in. If people didn't focus so much on that, I would never ask myself that kind of questions. And I also agree with what was said. I never felt any obstacle to the progression of my career, to be honest. The importance of role models can be extremely considerable. For example, if you take Laure Saint-Raymond and you look at her, you want to be like her. But indeed, as you said, the measures to be taken have to be extremely careful. Do you have another question? A last one, maybe, about Messiaen's music. Do you know whether he was conscious of mathematics or mathematical rules that were lied behind it? I don't think so. I don't think that he was really conscious or aware of that, except that in his writings he introduced attacks at irrational times, which is indeed a mathematical notion, but it's rather basic. Obviously, he was not aware of the link between non-retrograding rhythms and functional equations in Weil's theory. I can swear that he was not aware about that. I had a discussion with Pierre Boulez about the link between mathematics and music. Boulez, of course, was entirely aware of that link. But for Messiaen, there is a side of Messiaen which I particularly like, is the fact that he was an improviser. He sat at the organ of the Trinity Church in Paris and he improvised, and that was a miracle. Allow me to go from music to language. In 2018, you gave a conference in front of the Collège de France about mathematical language. And I remember a very interesting anecdote. You were mentioning a language that was created by a mathematician in the 1960s for a possible extraterrestrial communication. So are mathematics the only language of the real life? Is it a language? Is it a science? Is it an art? And behind it, the Platonician question, do you invent mathematics or you discover them? Well, this is an excellent question too. I hope I convinced you that the universe has a language, and that language is even a writing more than a language. And this writing is barcodes. Now, to turn to your specific question, are mathematics a language? No. They have a side which looks like language. And when we talk about mathematics, you forget to say, well, you mentioned physics as a language as well, but very often you forget to perceive and to say things that are extremely important, i.e., the mathematics are a place where you melt notions together. Within a certain mathematical community, these new notions are not communicated to the general public. But let me take an example of a notion that has become quite common, but was not to start with. The idea of function, a graph for a function. For example, if you take this sad example of the coronavirus, or politicians talking about inverting the curve of unemployment. You could use a derivative function for that. This notion of a function was initially totally mathematical, and it's become well known by the general public. Because writing about it made it possible to change a number into something tangible. The computer changed functions into graphs, and people can look at graphs and understand when they are being told that growth is slowing down, which is a second derivative in a way. These concepts have been invented by mathematicians, and then later on, progressively, they are being disseminated in society at large. This role of mathematics is absolutely vital. Many, many notions and concepts used in society have their basis in science. For example, the notion of energy or things like that. This is the most important role mathematics can play. To go back to your question, do we invent or do we discover? Well, I mentioned this mysterious spectrum. I'd like to be able to invent that kind of things, but it's not true. I have my computer with me, and my computer calculates for me. It's a reality. It's a very, very powerful reality, just as powerful and as solid as the chair I'm sitting on. It is a reality. You discover it progressively, and to understand it, you invent new concepts. What's very delicate is to make the distinction between a kind of archaic mathematics that is being discovered and is always goes always through integers, and concepts to understand them. If you can make the distinction between the two, that's good. To take an example that I find very convincing, nobody is going to say that when Watson and Crick discovered the structure of the DNA, they didn't invent it, they discovered it. Nobody would say the contrary. It existed before, but they discovered it because they used an electronic microscope, thanks to which they were able to see that structure. Well, in mathematics, it's just the same thing. There is a reality, intangible reality, and you have these tools that you need to understand this reality. If you make the distinction between the two, that's fine, and there is no problem any longer. There is no distinction between Platonicians on the one hand and realists on the other. Of course, you need to make that distinction, but in many cases it's a very subtle discussion. Anton, do you agree with that? Well, Alain is saying very valid things indeed. Mathematics is a universe in itself. It does indeed exist independently from us. We enter that universe. We discover stars and galaxies going around in that universe. But yes, indeed, I do believe that it exists independently from us. On that, I do agree. Well, I thank very much Alain for having indicated so clearly the difference between concepts and mathematical realities. I have a feeling that sometimes in mathematics you create something that can't be seen, but help us transcend what we can't see. So we discover things to be able to better understand. You need to create things that do not exist and that are very complex in a way in order to understand this reality. Alain Connes, you mentioned computers earlier on. Computers are indeed extremely helpful for mathematicians, and that reminded me the scenario of your novel Atacama's Spectrum, where artificial intelligence is considered as something diabolical because it beats the human being without human beings understanding why. I know that you are very critical towards that, and you mentioned that in interviews with the French media. Do you think that these algorithms are helpful for human creativity, or are they obstacles that have to be avoided at all costs? Well, it's very interesting indeed as a question, but you need to be very rigorous to answer that. I do use computers all the time. I have absolutely nothing against computers, quite on the contrary. On the other hand, I have a certain reluctance towards what is called artificial intelligence. The word intelligence doesn't suit me at all. The comparison I have is the following one. When Galois understood equations, what we call Galois' group and his theory of ambiguity. At his time, he was incapable of doing all the calculations, and he knew. On the 200th anniversary of his birth, I gave a conference in front of the Academy of Sciences. I gave an example at the end of an equation with a degree 5, and I made the calculations with my computer. The first coefficient of the polynomial that appeared on the screen was a number, a rational number, the numerator of which had 10 to the power 5 figures. It was therefore something that was huge, and no human being would be able to make such a calculation. No, I made a mistake. It's 10 to the power 500 for the numerator and the denominator. So that kind of calculations can be made instantaneously by the computer, and then you understand Galois' theory. So Galois was able, thanks to his intelligence, and I use the word intelligence in the right meaning of the word, to understand without having to do all the calculations. Now, when we talk about artificial intelligence or neuronal networks, what happens is exactly the opposite. These algorithms can do things without understanding. And I attended conferences about artificial intelligence, and I was struck by the fact that these algorithms could reproduce results from chemistry with atomic nuclei, etc., without using Schrödinger's equations. For me, it's a regression. It's going backwards. It's going in the wrong direction. You're able to do without understanding, whereas for me, the aim of the human species is to understand without having to do. So that frightens me. Precisely because of that. Because I believe that in the end, we won't understand a thing. Sometimes I receive emails, obviously coming from intelligence, artificial intelligence. They are asking me to being nominated for certain posts or functions, and it's totally irrational and totally crazy. You notice immediately that there's no intelligence behind it. So I think the risk is that we will be invaded by things that are not controlled by human beings. For the time being, if it happens on your computer, you think, oh, well, I made a mistake, my computer has given me a wrong answer. But let's suppose that artificial intelligence is behind you. You won't be able to understand a thing. It might be something coming from artificial intelligence. You won't be able to understand it. And I'm afraid by that. I must confess it. Maybe I'm an old-fashioned man. But this idea that it's called intelligence is something frightening. I don't think we shouldn't sell our soul to artificial intelligence. Obviously, some people will tell you it's very helpful in medicine. Yes, indeed, it is. What you use as a tool to recognize what's happening on an X-ray is extremely helpful indeed. But basing oneself only on artificial intelligence, no, I don't agree with that. That would be a terrible mistake. Some people talked about artificial stupidity, indeed. Well, you are quite right to say so. With the Go game, for example, a record has been broken, but the record of stupidity is going to be broken as well. I think that's already the case, as a matter of fact. We're closing this evening. Let me end with a few questions. The first one being that the methodological doubt, so dear to the heart of Descartes, that's what you mention in your novels. My question is therefore, since sometimes you need years or decades for mathematical theories to be admitted, do you need to doubt to be a good mathematician, or should you always be certain?
Excellent question. I live in doubt. I wake up every morning, 3 or 4 hours in the morning, and I wonder and I doubt. So doubt is fundamental, is essential. And that's how we can go further, and that's how the child develops. When the child starts to doubt, that's when the child starts to develop. It's in the frontal part of the brain that it's happened. And we are trying to, in fact, praise doubt. One very last question as a conclusion. It's a naive question. When I was reading at university, I could listen to mathematicians who used to say that's a pretty or a beautiful demonstration. What's beauty all about in mathematics, and does one need to be a mathematician to be able to understand the concept of beauty, or can everybody understand the beauty? Well, it's true that you need to be a mathematician, but when I made a presentation at Collège de France on language, I gave my version of the demonstration of Mole. If you take the underground and you see somebody reading a music score, so it's a bit opaque, but if you see somebody reading a page of mathematics, it's just the same thing. Why? Because that's what the mathematician's work is all about, is to create a mental image, i.e., the mathematician, one of his main activities is to try and work out a problem, because in trying to work out this problem, his brain is going to create this mental image. And then he will, having not found the answer immediately, he will now find out exactly where the demonstration is going to become beautiful and why it's going to become beautiful. So it is opaque, unlike music. You cannot play mathematics, you cannot explain the beauty of mathematics in such an obvious fashion. And I've tried in my presentation to show you the beauty. The Mole Theorem is so beautiful as such that that's enough. And you can see in the example of the Mole Theorem, any triangle, you cut out the angles and you look at the intersections, and it's an equilateral triangle. Because of any kind of triangle, you'll get this ternary symmetry, whatever way you look at it. So that's what's beautiful. It's a beautiful truth. So you can ask yourself, what is the beautiful demonstration? And we can discuss this at length. And for this, you need to go into the details. But you need to be a mathematician to be able to do so. Antoine, Elise, what about the beauty of mathematics for you? Well, I think that we become more and more aesthetically orientated as we read mathematics, and I think we have a very personal view of aesthetics. What I find beautiful in a demonstration, perhaps not seen in the same way by others, but as the Mole Theorem, perhaps there's certain degree of purity, and we're going to look for simplicity and purity in a development, and I think that explains the beauty of mathematics. If I may add my viewpoint, I agree with Alain and Elise. I think that we use the same concept of aesthetics to describe the beauty of mathematics, like we describe beauty in the real world. So perhaps we might not agree like we disagree in art, for instance, but as Alain used an example of classical geometry, and you can also use an even more simple example. There are dozens of demonstrations of Pythagoras' theorem, and everybody can have a look and decide which demonstration is most pleasing. And drawings are used, and you can decide which is the most pretty, the most elegant of all drawings. So that's a good exercise and a good example, because then you see this fantastic theorem and people are still looking for ways to prove it differently. And after several millennia after the discovery of the theorem, we can see and decide which is your preferred demonstration. I think the time has come to end the evening, and I'd like to thank all those who've taken part in the round table, the Wright Foundation, Professor Courvoisier, the University of Geneva, that's our host for this evening, and obviously heavily involved in the organization of the event. Just for your information, there was a light show that was supposed to take place at the end of the week, which unfortunately has been postponed given the pandemic. It's not been cancelled. It's going to take place in 2021, and you'll be given the dates if you check on the Colloquium website. And there is a virtual exhibition on mathematics, which is on the Colloquium website, Belle Math, beautiful mathematics. And we will meet up tomorrow evening with Olivier de Cibourg, who will introduce the speaker for Friday evening, Professor Smirnov from the University of Geneva, who is going to conclude this wonderful week entirely devoted to mathematics. Thank you very much.